So let's start out by just giving you a rough outline of what the seminar is planned to look like. And then I want to give you 3 or 4 different ideas or areas where I think that units could be developed from. So the seminar will start with understanding the biology of pathogens and human infection. We'll move on to covering the routes of transmission, things like how does a person get a cold. We'll cover technical concepts like how do you disinfect a place for viruses and how does the chemistry of that work. We'll think about the transport of viruses. How long does it take for a virus to settle into the ground once it's been aerosolized, as well as other technical aspects of the virus, including its biochemistry. We'll also discuss the social and political concepts of infectious disease, and specifically respiratory infectious disease. Now, the infectious disease world is very big. And so I've tried to narrow it down by mostly focusing on viruses and focusing that even a little bit more into respiratory viruses. Now, if you have a virus or a disease that you're interested in that doesn't fall into that categories, that doesn't mean it's not suitable for a unit, but it does mean that most of the teaching in the course and most of the discussion will focus on respiratory viruses. And so you may not be able to get all of the learning out of the seminar that you would if you were to go with a respiratory virus. So the seminar will be well suited for teachers, junior high students and high school students in the science as well as the humanities, because we're really going to hit on these social and some political concepts of disease outbreaks, pandemics, etc. The material in the seminar could also be made suitable for units written by elementary grade teachers. My past experience has been that I've been impressed and a bit in awe of the clever ways that elementary school teachers have taken what I think is some pretty difficult concepts and made really excellent units for their elementary school classes. So I look forward to people trying to do that. I know that teachers were going to bring their experience and their knowledge to build creative and appropriate units, and I'm interested in what you have to offer in terms of ideas. But here are just a few thoughts about how you might be able to structure units. If you're a mathematics and statistics teacher, well, epidemiology turns out to be almost all mathematics and statistics. I'm showing you an example of a COVID-19 outbreak in Bridgeport, Connecticut. What you're looking at is what has been modeled as the actual outbreak, the number of cases per population over time. And it was modeled based on wastewater COVID concentrations and this multivariable regression that was developed elsewhere. And you can see when you actually look at it with the measured cases, the actual measurements, it's the same in timing and the same in magnitude. This is all, again, just to show you that you don't have to think about regressions for this unit as much. But what I want to convey is that much of the work in infectious disease is mathematics. It is statistics, it is calculus, it is algebra. It's the basis of epidemiology is mathematics. So there's a lot on the political and social implications of infectious disease, just mainly because it has such a huge toll on our health, our morbidity, as well as our mortality, and certainly on our economics. This is a graph that shows you when the world reached 5 million COVID-19 deaths. And what you can see is that the Americas had many, many more deaths than Africa, even though the population of Africa is larger than North America and South America put together. And it's interesting to explore why that is. What were perhaps the cultural differences, the differences in behavior, the differences in governments that caused that? There are many other political and cultural questions to explore. We were all faced with these during the last COVID-19 pandemic as well, thinking about what do we do when our institutions are no longer trusted by the general public? Why were our institutions not necessarily trusted by the general public? And how can we, solve those types of problems? So from institutions to physics, this routes out the transmission of an airborne disease, something like, let's say, RSV or some forms of influenza. And what you're seeing is particles, and these particles are kind of big in this case, and they settle down to the ground fast. These particles are small and they stay in the air. That's just pure physics. Why does a really small particle stay in the air versus a really large particle fall down to the ground really fast? It has to do just with gravity and the laws of gravity and Newton's laws mostly, but we add in the element here of wind resistance. Turns out wind resistance isn't a very big thing if you're a large particle, but it's a huge thing if it's a small particle. And it's all fit together by a force balance on a particle called Stokes' law. Now, lest you be a chemistry teacher, we have lots for that as well. And I'll just give you an example, thinking about the disinfection of viruses. Remember us walking around during cold and flu season, during COVID-19 with a box of Clorox wipes or all the hand sanitizer we put on our hand. Those are first order reaction rates. If it's chlorine as a disinfectant, then it's simply hypochlorous acid that gets oxidized to chloride and oxidizes everything else in its way. Hypochlorous acid can transform into hypochlorite at a higher pH, and one is a much better disinfectant than the other. But I think the chemistry teachers among you can hear this and think about this and can probably find a lot of interesting chemistry in not only the disinfection of microorganisms and pathogens, but also the biochemistry of these pathogens. One final slide that I'll put forward is just the biology and the evolution of viruses. So this is a rich field if you're a biology teacher as well. So again, there is just the plain biology of the viruses, how they survive, what kind of mechanisms they use, what their biology and biochemistry looks like. But then there's the evolutionary side of it. And the evolution of viruses is a really interesting scientific thing. I'm showing you a graph here that's well known, and it shows that higher level eukaryotes, these are people and monkey and fungi and algae and things like that, and plants, have very large genome sizes, and they don't mutate very fast. Their mutation rate is very slow. That's why it takes us so long to evolve. Things like viruses, though, have very small genome sizes, and they mutate at a very fast rate. They can mutate very fast. In fact, we all, again, have experience with this, just given the different types of strains of COVID that popped up over different times during the pandemic. So what are the implications of that? How does evolution play a role in jumping from animals to humans? What's going to go on with bird flu, and how is evolution a part of that? There's a lot of interesting things to study there as well. So I hope this was helpful as a primer on this course, and gives you some ideas about what units that you might want to go after and propose. I would say that the reading in this will be set a little bit later, but we're going to read a book about viruses that's a relatively short book, and then we'll have specific readings on the different topics that are relevant for viral respiratory disease and the modern kind of seminar understanding of them that I think will be helpful for you in writing your units. You should have all my contact information. I look forward to seeing your proposed units, and I look forward to meeting you all again in May if I haven't met you, and certainly seeing some old friends again. Thanks.